Is that cool? All right, Jacob, will you be our puller backer again?
Yeah.
I got to change the camera view. All right, so now you are all going to need this data. So get your computers out so you can record the data on your computers right now, or feel free to, if you don't want to do that, then feel free to just write it down. But you're going to need the data in a moment. And I'm running out of whiteboard markers. That's a good idea. Now, we'll give a bonus point. If you don't pull it back at all, what's probably going to be true about the speed? It's probably going to be 0. So let's put 0, 0 in just for fun. All right, Jacob, are you ready? All right, so pull it back 3 centimeters. All right, I got 0.46. So first data point, you pulled it back 0.03 centimeters, and 0.46 was your speed. That looks good. All right, let's go 6 centimeters. I like doing labs with Jake. He's a great lab partner.
Thank you.
No, Jake. Thank you. Oh my God. Just when. Just when. Um, 0.86. So you said that was 6 centimeters? 0.0686. All right. So let's go to 9 centimeters. Oh, pull it back, 9. Um, 1.22. And last one, 12 centimeters. This is the big one. 12 centimeters. Oh. Jacob is the best lab person. So put one hand on the front and one hand on the back. Okay, 1.80. All right. So we have our data. Bring up the end plot. Put it in. All right, and let's see if we can get it done. You know what I find interesting about this is I wonder if we can't, before you guys get too far into it, I wonder if we can predict what this might look like. Like, for example, if this were a linear relationship, what would be true about the data? Okay? If this were a linear relationship, what would be true about the data?
As the pull vector stance goes up, the speed goes up.
Sure, he says, as these go up, these should go up, which is true. If it's linear, they should go up by the same amount. For example, between 0 and 0.3, it went up 0.46. This is another 0.03. Well, 0.46, another 0.46 would give you like 9.2. This is close. And like another 0.03, does this give you another 4.6? Well, another 4.6 would give you 2.8, and we got 2.2. That seems pretty reasonable. Or another way to think about it is, if you double this, does this double? So I go from 0.03 to 0.06, that's times 2. This is close to times 2. This is times 3. This times 3 would be 3.2, and I got 2.2. This is times 4. This times 4 would give me 84, and I got 80. So, I don't know. It might be linear. It might be linear. What happened? It's beautiful. What's wrong with it? Well, this is the best bit of line. I mean, I don't even know how close he was looking, but, you know, like, oh, I mean, it's not quadratic, right? It's not curving up or curving down, right? I think that looks linear to me. What do you think? What's the slope? Go back to envelope. What's the slope? 14.5? Okay. Seems a little high, but we'll let it go. All right. Good. Beautiful. All right, take a moment and finish the analysis. Gotta try to figure out what time is. Oh, 05. Okay, we got 8 minutes. Other comments? Very nice. Good. Get it into the document. Get it into the document. Oh, we're not enabled today? You don't have a computer, you guys can always use any of mine that are right back there. I got 6, 7 back there. Feel like you can jump on them. Just do it. I would do that so it's done, so you don't have to do it later. Lots of whiteboard markers from home. Orange, purple, brown, 2 greens. I'm now green enabled. Love that. Love being green. Now I have more green than anything else. I've been busting them out. All right. So as you guys finish up the analysis, let me show you what we're going to do tomorrow, just as a quick preview. As a quick preview. If you'll notice on the assignment, there are actually 2 slides. Can you see the 2 slides on there? The next slide is exactly the same, only different. So what we have, our situation looks like this. Where, in essence, we have a cart. And we're pushing it back against the spring. Now, I know we're pulling it back against a rubber band, but we'll just have to pretend. And then over here we're looking. Right? And so what we actually measured was how far back we pulled the spring. We call that the pullback distance. And then measured the speed of the car. So those are the 2 things we measured. And you're plotting them, and I'm looking at all your things, and it looks pretty linear to me, which I think is so cool. Like, think about, if I wanted to go twice as fast, all I got to do is pull back twice as far. How cool is that as an idea? I think it's fascinating. But what I'm really interested in is not those 2 things. I'm really interested in the energies. So where is the energy stored when I pull it back against the spring? Stored in the spring. What do we call that? We call that elastic energy, right? And then when it's moving, we see it in the motion of the object. What do we call the energy of motion? That's the kinetic energy, correct? So I want to know, if I plotted elastic energy and kinetic energy, what that graph would look like. That's what I really want to know. Well, how are we going to find the elastic energy? Well, from our studies, we know it's 1/2 little k x squared. And kinetic energy is 1/2 mv squared. So, in order to find the kinetic energy, what 2 things do I need to know? The mass and the speed, right? The mass of the car, we can just measure. It's about 1/2 kilogram. What's the other thing we have to know? The speed, right? Don't you have that in your data table already from the other slide? So we're just going to calculate each of our kinetic energies and put them into the data table. Cool? What about the elastic energy? We need to know 2 things. We need to know the spring constant, which I'm going to tell you. No! All right, we're going to assess tomorrow, and then we're going to finish this lab.
Okay, so 2 questions. So we're gonna finish the second slide tomorrow?
Yes.